Hello everyone, my name is Abdulrahman from Osaka University, Japan. At the beginning, I would like to thank the organizers for this opportunity to present my work. Today, I'm going to talk about mechanisms of thermal atomic layer etching of nickel by acetylstone molecules. As you know, semiconductor technology feature size is reducing year by year. Nowadays, micro devices have reached VO nanometer scale dimension, as you can see here. Therefore, we need some technologies that can be used to fabricate these devices precisely. Atomic layer etching is one of these technology can be used to etch can be used for precise and damageless etching of materials layer by layer. We have two type of ALE, plasma enhanced ALE, which is out of the scope of this work, and thermal ALE, which I'm going to explain today. Also, as you can see here, metal and magnetic materials need extreme care during etching processes, especially when they are used in nanoscale devices, because it is prone to damage due to ion bombardment during the reactive ion etching processes. One of the applications of this problem or of this issue is etching MTG stacks of MRAM. So as you can see here, it is around 10 nanometer. As you can see here, it contains some metals separated by some isolated layers, as you can see here. So we need some technologies that can etch these materials precisely. Dry thermal atomic layer etching is the most promising method that can be used to fabricate nanoscale devices precisely. So let me, at the beginning, explain what is the thermal ALE. So if we have like the metallic surface, as we can see here, we have the nickel, and we want to etch this surface. So first of all, we started with the modification step where we oxidize the surface to form nickel oxide layer on top of the surface using oxygen gas. Then when the surface is exposed to the etchant gas, it can be some beta decatone gases. For example, here we are using hfacH gas. The nickel complex will be formed and it will be volatilized, and H2O, as you can see here, to remove this nickel oxide surface by increasing the temperature of the surface. After we remove the nickel oxide surface, as long as we are still pumping the the etchant gas will be dissipated, and because it doesn't interact stably with pure metallic surface, and this is what is called the self-limiting in these processes. So if we want to keep etching this surface, as you can see here, we need to repeat oxidizing step following by the exposure of the etchant gas step and increasing the temperature to remove the oxygen atoms by H2O and the metal atoms by the nickel complex, as you can see here. And by repeating this step, the metal can be etched, as you can see here, until we reach the isolated layer. Etching the isolated layer here, the magnesium oxide, is out of the scope of this work, and it has been discussed in this work. You may look to this reference if you are interested to know this. Also, I have already published these three papers that can explain the thermal ELE of nickel by another beta decatone, which is hfacH. So we started with a simple model, then we went to more realistic models, as you can see here. So as I mentioned, we have done the job for hfacH, and we want today to investigate the mechanism of thermal ALE using acacH. So as you can see here, the difference between acacH and hfacH, these CF3 groups are replaced with the CH3 group. So from this study, we want to know what is the mechanism of thermal ELE of nickel with acacH. The second objective is what is the difference between hfacH and acacH in thermal ELE processes. The third question that we want to know, which one is more favorable gas for thermal ELE? I'm going to answer these questions using the first principle calculations based on DFT. For these calculations, I'm using TURBOMOLE, and this is the used model, as you can see here. The middle of this big cluster, I'm treating the atoms quantum mechanically. However, I have replaced the nickel atom with +2 and the oxygen atoms with -2 to mimic the valence electrons. And for the simplicity, I have replaced these atoms. So also for those who are interested in DFT calculation, PPE functional is used with DF2 SVP basis set for nickel and magnesium, while DEF2 TZVP is used for other atoms. Also, I would like to mention D3BJ dispersion correction is used to increase the accuracy of this work. So let's see what we have found. So when the acacH reaches to the surface, this molecule is deprotonated and this hydrogen is transferred to the surface and the reaction energy goes to -1.94. When another one also, it's same, it is deprotonated and reaches the reaction energy -3.57 eV, but unfortunately, the nickel complex cannot be formed on a flat surface. After that, we have tested the desorption energies. So if we assume the H2O dissolved first, we need 1.24 eV, and the reaction energy will increase to -2.33 eV. However, if we assume the nickel complex is dissolved first, as you can see here, the reaction energy increased to 1.11 eV, which means the needed energy is 4.68 eV. So it means the H2O will be dissolved first. After that, this nickel complex will be dissolved. And in that case, the reaction energy goes to 2.19 eV, and the needed energy to dissolve this nickel complex is reduced to 4.52 eV. From these calculations, we can plot the energy diagram. As you can see here, we reach the most stable state when both of them are adsorbed, and the reaction energy goes to -3.57 eV. Then if the surface gains some energy, as we said, it is thermal ELE, which means by heating the surface, the H2O will be dissolved first, then the nickel complex. If it's gained too much energy, the nickel complex can be dissolved as well, as you can see here. Also, from our previous work, we decided another model that can be used to mimic the rough surface. So here we have added 5 nickel oxide molecules on top of the surface. And when the acacH reach to the surface, they are deprotonated, as you can see here, and interact stably, forming the nickel complex on top of the surface with the reaction energy -4.71 eV. Again, we have tested the desorption energies. So if we assume the H2O will be dissolved first, the reaction energy increased to -3.66 eV, which means the needed energy is 1.05 eV. However, if the nickel complex is dissolved first, as we can see here, the reaction energy increased to -0.75 eV, which means the needed energy is 3.96 eV. So the H2O will be dissolved first. After that, this nickel complex will be dissolved to reach the reaction energy -0.09 eV, and the needed energy reduced to 3.57 eV. So from these calculations, also we can plot the energy diagram, as you can see here, with the most stable state is to form the nickel complex on the rough surface, and as you can see, the reaction energy went much lower to minus 4.71 eV. And if we heat the surface and gain some energy, the H2O will be dissolved first to reach this reaction energy minus 3.66 eV. Then also by if the surface gained more energy, it's like we found here, it's around 3.57 eV. This nickel complex will be removed, and like this we have removed nickel oxide from the surface. So we want now to compare these results with our previous results that we obtained with hfacH, the other beta D ketone molecule. So the main difference here, as you can see, with hfacH, the needed energy is much lower. The needed energy to remove the nickel complex that is formed by acacH. Also, I would like to mention another thing here is that the fluorine atoms are negatively charged. So they are going to repulse, even if this nickel complex is tilted to the surface, they are going to repulse with the oxygen atoms, which keep this nickel complex stable on top of the surface. However, in case of acacH, these hydrogen atoms are positively charged, which allows this molecule to tilt more to the surface and then allow these carbon atoms to interact with these positively charged nickel atoms of the surface, which may cause the decomposition of this nickel complex, which has been observed experimentally. So this is the last slide in my presentation. So let me summarize my work. acacH gas can be used for thermal ELE of nickel after it is oxidization step. The mechanisms of thermal ELE of nickel by acacH is similar to the one by hfacH, which means the investigated mechanisms can be generalized to 3-fluoroacetylacetone gas, which is another type of beta decatone molecules. The last point here I have, hfacH is more stable on a nickel oxide surface because the negatively charged fluorine atoms in hfacH repulsed with oxygen atoms in the nickel oxide surface. So they don't allow carbon atoms in hfacH to interact with nickel atoms. Unlike the positively charged hydrogen atoms will go closer to oxygen atoms of nickel oxide surface, which allows carbon atoms in acacH to interact with nickel atoms, which cause it is instability. As a result, hfacH is the best beta decatone gas for thermal ALE. At the end of my presentation, I would like to thank JSPS Grants in Aid, Core-to-Core program, research fellowship for young scientists program. And thank you for your attention. And this work now is open for your questions.